Good day, everyone. Last time we embarked our Bayesian journey by introducing the whole philosophy of modeling and the parameters that we want to estimate as random variables and assigning a prior distribution to them. We studied in a certain degree of detail the so-called MMSE estimator, which, remember, is the one that minimizes the BMSE, the Bayesian mean square error, okay, which we defined as the expectation of the square distance between the true value of the parameters and the estimate, okay. This can of course be written as the expectation of the square norm of the error. We define the error in this way. Today I would like that we start by reflecting on the symmetry that this performance metric exhibits, specifically its spherical symmetry. So to that end, let us suppose that theta is fixed, okay, and let us look at the set of all estimates for which this square norm is the same, okay. So for instance, suppose that theta is 0, and we are interested in the set of estimates for which this square distance here is 7, let's say. Then obviously that set of estimates forms a sphere with a center at 0 and radius square root of 7, right? So there's here a spherical symmetry. To the eyes of this metric of the BMSE, it doesn't matter what is the direction of this error. It just matters its magnitude, right? So how far we are from the true estimator, from the true value of the parameter. Sorry. However, this form of symmetry does not really emerge in many practical situations. So this could be a very simple example. Suppose that you would like to jump to the other side of a hole on the ground. So since this is a mental experiment, we can assume that the hole is infinitely deep, okay? So let's look at the cost of making of the estimation errors, essentially. So as on the one hand, let's look at the cost of overestimating the width of the whole theta. So if this width is for example 2 meters and our estimate is 2.5, okay, then okay, we will manage to jump to the other side. Perhaps it would have been better if our estimate was exactly 2 meters, right? Because, okay, if we overestimate it, then we spend more energy, okay? Or so perhaps we need to eat a little bit more, but everything is all right in that case. However, if we underestimate theta, then we, for instance, theta is 2 meters as before, but our estimate is 1.5 meters. Then we fall in the hole and we die. Okay, so the cost is not symmetric in this case. So 50 centimeters in one direction is totally different from 50 centimeters in the other direction, right? So therefore, if you would like to solve this estimation problem, you'd better not use the BMC as a metric, okay? Instead, it makes more sense to look into something more general, such as, for example, the so-called base risk. The base risk is defined as the expectation of a loss function that in principle we are free to choose to suit the needs of our problem. This loss function must quantify the cost that we suffer when the true value of the parameters is this, and the our estimate is this one here. So this obviously generalizes BMC, right? If we set this loss to be this square distance, right? This would be the so-called quadratic loss or square loss. Then obviously this right-hand side coincides with this term over here, and therefore the base risk equals the BMC. Okay, so this can be visualized in our previous example. If we plot the square loss as a function of theta hat for a fixed theta. Okay, so note that it has two arguments. So this is obviously a parabola with a root at theta hat equals theta, equal to theta. And here we can corroborate that the cost of underestimating, let's say, theta by 1 meter is the same as the cost of overestimating it by 1 meter. Okay. So this loss doesn't really make sense for this problem. We can think of more natural loss. For example, we could set the loss to be a very large number when theta hat is less than theta, right? And we can set it to be, I mean, it's natural to set the loss to be 0 if theta hat equals theta, right? Perhaps we don't have loss, right? Cost or extra cost, let's say. And whenever theta hat is greater than theta, it makes sense to set this to be some increasing function, right? Because as we said, overestimating theta has some small cost in terms of additional energy consumption, or perhaps an increased risk for our joints or something like that. For each possible choice of the loss function, there will be an estimator that minimizes the resulting base risk. So let's look at some examples. The first one is the loss that we saw in the previous slide, the quadratic loss, right? Defined in terms of the L2 norm or Euclidean norm in this way, right? This is clearly the sum of the square differences between each parameter and its corresponding estimate. This can be visualized for the case of when we have only one parameter. If we plot L versus the error defined in this way. This is clearly a parabola with a root at the origin. And now we can just put together two facts. One fact is that the BMSE and the base risk coincide for this specific loss function, as we said in the previous slide. And the other fact is what we saw in the previous lecture, that the estimator that minimizes the BMSE is the posterior mean, right? The mean of the posterior distribution. And with these two facts, we conclude that this is also the minimum base risk estimator for the quadratic loss, okay? Another possible loss is the so-called hit or miss loss, which is zero when our estimate is sufficiently close to the true value of the parameters. Here, delta must be understood as a small positive constant, and it is 1 otherwise. So it is a loss that really cares only about whether our estimate is very good, otherwise it doesn't care much. In the case of one parameter, this could be illustrated in this way. It would take the value 0 in the interval minus delta delta and the value 1 elsewhere. And it can be shown that the minimum base risk estimator for this case is the one that maximizes the posterior PDF, right? So this is in the terminology of probability theory, the maximum of a PDF is the mode, right? So then we see here another example of minimum base risk estimator. And another possible loss, also widely used, is this one here, where which is the L1 norm of the difference between the true parameter and the estimate. So this, by the definition of L1 norm, this is nothing but the sum of the absolute values of the differences between the true and estimated parameters. In the case of only one parameter, we can plot this loss versus the error, and it will look in this way. It has a V shape, because it's an absolute value. And it can be seen that the resulting minimum base risk estimator is given by the median of the posterior PDF, right? So remember what the median is. The median is the value that divides the entire range of values of a random variable into two sets with equal probability, right? So the probability of a random variable being less than its median is 1/2, right? And the probability that it is greater than its median is 1/2, right? So it splits a PDF into two parts with equal area, essentially, right? So this makes a very neat picture. For this estimator is the mean, this one is the mode, and this one is the median of the posterior distribution. It is interesting to note that both estimators, these three estimators will coincide in the case of that the posterior is Gaussian, right? Because as we know, for a Gaussian distribution, the mean, the mode, and the median coincide. So in the rest of this lecture, we will focus on this estimator, the mode of the posterior, which is called the maximum posteriori, right? So this we presented or used the hit or miss laws to arrive at this estimator, but I mean in practice we just use this estimator without mentioning the hit or miss law. So it's not really important to remember this concept here, but it will be important to know what this estimator is and how to compute it. As we said, the maximum a posteriori estimator finds the theta that maximizes the posterior, right? The posterior PDF. And as we already said a couple of times earlier in the course, maximizing a function is the same as maximizing its logarithm, right? And this is just a consequence of the fact that the log is an increasing function. So now one can just use our working definition of conditional PDF to express this objective function in this way, okay? And applying again the same definition allows us to rewrite the numerator in this form here. So this is precisely what we did in the previous lecture to express a posterior PDF in terms of the likelihood, the prior, and its normalizing coefficient, okay? Now just applying the properties of the log, and by noting that this term here, this p of x, does not depend on theta, right? What we are left with is this objective function here, okay? So the first thing we need to note is that this is precisely the objective function maximized by the maximum likelihood estimator, okay? And so this, remember that the maximum likelihood estimator is a non-Bayesian estimator. Therefore, it just looks at the data. It doesn't take into account any prior information about the parameters, right? So essentially, this term condenses what the data says about theta. And this second term is a term that does not depend on the data, it depends only on the parameters, right? And as such, it is typically referred to as a regularizer, especially in the machine learning literature. So this term essentially will promote estimates that agree with the prior information, right? Estimates for which this prior is large, right? In contrast, this one promotes estimates that explain well the data, that agree with what the data is saying, right? So therefore, this is again an example of can be interpreted in the same way as we interpreted MMSE estimators in the previous lecture, right? So Bayesian estimators essentially combine what our eyes tell us with what we know beforehand. So essentially, we can think of the maximum a posteriori estimator as sort of an extended version of a maximum likelihood estimator that also accounts for the prior information. So it's sort of the Bayesian counterpart of the maximum likelihood estimator. And here a couple of remarks are in order. First, remember that the MMSE estimator is the posterior mean, okay? And as therefore it is an expectation, right? So an integral, right? And in certain cases, one can solve that integral in closed form, okay? And therefore, the resulting MMSE estimator can be typically easily computed, right? However, in the general case, one cannot solve that integral in closed form, and therefore one needs to resort to numerical integration. But integrating a function in many variables is something very difficult. Even integrating with respect just to a few variables, it may be challenging from a computational point of view, right? So MMSE estimators can be, take quite some, a large number of, may take a large number of arithmetic operations, essentially, right? In contrast, maximum a posteriori estimators are found as solutions to optimization problems, and optimizing is from a numerical perspective much easier than integrating, right? So therefore this constitutes an important strength of maximum a posteriori estimators relative to MMSE estimators, okay? The caveat is that even solving this optimization problem may be too difficult sometimes, right? So think, for example, that this objective function may have multiple local optima, multiple local maxima. So it is difficult to find the global maximum, right? And therefore, what we may end up with is not the true maximum a posteriori, but we just use a local maximum as a surrogate for it. So indeed, solving non-convex optimization problems is also a very difficult task from a numerical perspective. But as we said, we can typically cope with that just by using local optimum. But of course, the results will not be are not expected to be as good as if we use the global optimum. So let's look at a couple of examples. In this first one, we have a Gaussian linear model where theta has this prior distribution and W is white Gaussian noise with this power. And theta is independent of W as always. To obtain the maximum a posteriori estimator, we need to maximize the log likelihood plus the log prior. So the log likelihood can be found as in previous lectures. Remember that the conditional PDF of x given theta is given by the exponential of this term divided by a constant, and therefore when we take logs, we arrive at something like this. This is a constant because it doesn't depend on theta, which is our optimization variable. The log prior can be found by taking the log of this PDF here, okay, and therefore for the same reason it is given by this. The maximum a posteriori estimator therefore maximizes this term plus this term here. And this expression can be simplified by multiplying this objective by -2 sigma w square, right? And therefore the coefficient that multiplies the first norm becomes 1, and the coefficient that multiplies this second square norm is plus 2 sigma w square divided by 2 sigma theta square, right? Which is sigma w square divided by sigma theta square. And this is precisely what we called lambda here. And we need to change the maximization with a minimization, and because the number that we use to multiply the objective function is negative, right? So let us interpret this objective. Here we see that the first term depends on both the data and the parameter, right, as we saw earlier. So this can be seen to be small when theta agrees somehow with the data. So to see that, suppose for a second that there's no noise, so w is 0. In that case, x equals h times the true theta, right? So if we substitute that here, we will obtain h times the true theta minus h times this optimization variable, which we also call theta, just to simplify the notation, as we already said multiple times throughout this discourse. So therefore this term is small when theta is close to, or when this candidate theta is close to the true theta. Okay, in that case we say that theta explains well the data, or agrees with the data, and this is why we call it a data fitting term. Okay, and the second square norm here, we see that is small when the candidate theta is close to the prior mean, right? So this is sort of our best guess of theta if we didn't observe any data at all. So we see again, as with MMSE estimators, that this objective balances two different criteria, let's say. So, or there are two forces here, and the map estimator will find a sweet spot between them. So on the one hand, this term pushes theta in the direction of what our eyes say, and on the other hand, this second term pushes theta in the direction of what our prior information says. And the balance is set by lambda, right? Which it's very natural if we think about it. So, for example, if sigma w is large, right, meaning that our x is very noisy, or if our sigma theta is small, meaning that our prior information is very certain, right? In that case, lambda is large, and therefore the optimum of this objective will be close to the optimum of this second term. Okay, so this is natural if the data is noisy and or our prior information is very certain, then we rely more on the prior information. And the opposite happens if our data has a little noise, or our prior information is very uncertain, right? In that case, lambda is small, and the optimum of this objective will be close to the optimum of this first term alone. To solve this optimization problem, we therefore need to take the gradient with respect to theta, okay? And if we do that, we obtain this expression. If we set it equal to 0, we can just rearrange terms to arrive at this equation, and solving for theta yields the desired map estimator. So here there are several observations that we need to discuss. First of all, as we need to draw connections with what we discussed in the first part of the course. Specifically, if we see that if we set lambda equal to 0, what we recover here is the least squares estimator. Okay. So does that make sense? Well, we can think when is lambda 0 or close to 0? Well, we see from here that this occurs when sigma theta square is large, right? And what happens when sigma theta square is large? It means that our prior information is very uncertain, right? If this goes to infinity, this is like having no prior information at all. And in that situation, this Bayesian Gaussian linear model would boil down to the non-Bayesian Gaussian linear model, right? For which the least squares estimator is was designed, right? So it actually coincides with the maximum likelihood estimator in that scenario. So it totally agrees. We see that it generalizes the least squares estimator. The second observation is that because of this matrix that we are adding here, we no longer have issues with the invertibility of this matrix. So remember that when we talked about least squares estimators, we needed to require that this matrix H had linearly independent columns, right? We call that the identifiability condition, right? Because otherwise H transpose H is not invertible, and we couldn't compute the least squares estimator. However, and now this matrix is always invertible, and to see that, just remember from linear algebra that H transpose H is always positive semi-definite, therefore it has non-negative eigenvalues, and when we add scaled identity, the effect is that lambda is added to all the eigenvalues here. So the eigenvalues of this matrix in brackets equal the lambda plus the eigenvalues of this matrix, and therefore all these eigenvalues, the eigenvalues of this matrix are strictly positive, and as we know, that implies that the matrix is invertible. Okay, so that means that we do not have any identifiability issue here. We don't have to worry about that. And the third observation is from of a numerical nature. Even in the case where the columns of H are linearly independent, they may be close to linearly dependent, right? In let's say in formal terms, it means that this matrix is poorly conditioned, right? And therefore, the eigenvalues of this matrix are small, at least some of them. Therefore, if we just invert this matrix, we get something with very large eigenvalues, and that it messes up our entire computation. So least squares is not a good idea if H is poorly conditioned, right? However, now since we are adding this scaled identity, even if this H is poorly conditioned, the eigenvalues of this matrix in brackets will be sufficiently far away from zero, at least if lambda is sufficiently large, right? And therefore this doesn't suffer from poorly conditioned matrices H. So we actually can use this expression instead of least squares for that situation. So in practice, I mean, you don't need to have any Gini giving you a prior distribution on theta. Whenever you are working on something and you are obtaining, you are computing a least squares estimator, if you see that these red letters or orange letters in MATLAB saying that the matrix is that you are trying to invert is poorly conditioned, then what you do is to go there and add a scaled identity to that matrix. And okay, instead of doing ls, you will be doing a map for some prior distribution, but you will be doing the job. I mean, what changes is perhaps a little bit theoretical interpretation, but you will get a much better estimator than what you get when all these yellow letters show up on the screen. This is another example. We also have a Bayesian linear model, but in this case the prior on theta is not Gaussian, but it has this form. This is what we call a Laplacian prior. So remember that a Gaussian PDF is an exponential of minus a positive definite quadratic form, right? And then divided by a constant. A Laplacian PDF is the exponential of L1 norm, essentially. So we don't have squares here, and then normalized by a constant. Okay. So again, theta and w are independent. So to obtain the map estimator, we need both the likelihood and prior, and the likelihood is exactly the same as before because it only depends on the probability on the PDF of w, which is the same as before. Okay, and then the log prior is the log of the joint and distribution of the thetas, which, since they are independent, is just the product of the marginals given in this way, right? So this can be written in this way by substituting this expression here, right, and using the properties of the log. And this can be simplified further in this way. So we have minus 1 over b times this L1 norm plus a constant. Okay, that's missing in on this slide. So the maximum a posteriori estimator is like just following the same procedure as in the previous slide, and given by the minimizer of this expression. So before we had a square to norm, now we have L1 norm without any square. Okay. This objective, or this optimization problem, has a name. It is known as the Lasso, which stands for least absolute shrinkage and selection operator. Okay, so this got very popular some years ago. And it in general needs to be computed numerically. It doesn't have a closed form. The good news is that this is a convex optimization problem, and those kind of problems can be solved efficiently. In fact, there are many efficient algorithms for this specific problem, and therefore it can be solved very easily. So although we cannot find a closed form expression to interpret it, it is possible to look into some special case to gain some intuition. So suppose that H is the identity matrix, right? In that case, we see from here that each entry of X is just a noisy version of the corresponding entry of theta, right? So we are just observing noisy versions of the parameters. If we just substitute it here and just apply the definitions of these norms, this can be written in this way. So here we have the sum of functions, and each function only depends on one of the parameters. So we can just optimize each one with respect to the corresponding parameter. So instead of doing a joint optimization for the entire objective function. And it can be shown that the solution is given by this, okay, by this theta m star. This is something that you can work out if you know the theory of subgradients, and it's a good exercise to do, but of course not necessary in this course. This receives the name of soft thresholding function of xm. Okay, it can be visualized in this way. We see that whenever xm is in this interval over here, the resulting theta m will be 0, right? And whenever it is greater than lambda halves, right, the output is not lambda halves, but not xm, but xm minus lambda halves, right? So this is what we have here, xm minus lambda halves. So it effectively shrinks the xm's that are greater than lambda halves. The opposite, the same happens in if they are xm is less than minus lambda halves. In that case, it's also shrunk towards 0, right? And this this flat region setting the small ones to 0 is what one can call selection, right? So this is why it's called shrinkage and selection. So this has the effect of making the estimate sparse, right? So sparse, we say that a vector or a matrix is sparse when many of its entries are exactly 0. So we see here that there will be potentially many zeros in theta, right? Even though our x may not have zeros, right? So this makes sense if we know that our true theta has many zeros, or many of our parameters are 0, right? This is actually something that happens in many problems, and it essentially gave rise to research topic that became very popular for a few years earlier, perhaps 10 years ago, something like that. So this is called compressed sensing, and this has been applied virtually to every research area, right? So there was some time where everybody was publishing papers on applying these sort of concepts to a specific application, right? So this can be used, I don't know, for instance, for reconstructing images in using MRI, or in wireless communications, in sensor networks. Everything can be used in this way, so long as you formulate a problem in terms of a sparse vector of parameters. And to conclude, let's wrap up what we have discussed today. We started by introducing the notion of base risk, which is a generalization of the BMSC that allows us to use custom losses. So we can freely select a loss function that quantifies our or the cost that we suffer for each value of the estimate given the value of the true parameter. And we looked at multiple examples of loss functions. One of them was the hit or miss loss, that we said that it results in the so-called maximum a posteriori estimator. It is called in this way because it maximizes the posterior PDF. So it is the mode of the PDF. It can be interpreted as a maximum likelihood estimator regularized by the log prior. So it essentially extends the maximum likelihood estimator to the Bayesian setup. And we considered a couple of special cases or examples. One of them was ridge regression. In this case, the maximum a posteriori estimator generalizes the least squares estimator, and it doesn't suffer from the conditioning problems and doesn't require identifiability assumptions. We also discussed the Lasso estimator, which is used whenever we know that the vector of parameters that we want to estimate is sparse, so it contains many zeros. So what is coming up is to see what to do when even obtaining a maximum a posteriori estimators is too difficult because of the optimization problem involved, right? We saw that maximum a posteriori estimators are easier to compute than MMSE estimators in the general case, because optimization is easier than integration, right? However, even optimization may be difficult, especially because of the presence of local optima. So we will be addressing this in the next lecture. And another set or limitation of both the maximum a posteriori and MMSE estimators is that they require full knowledge of the distribution of the data and parameters. However, it often happens in practice that we don't fully know such a distribution. We only know it partially. So, for instance, we only know moments like means and covariances. So, as always, I don't answer the questions today, so we'll discuss them in the next lectures. Thanks so much for your attention.